Hello. Let's do the second example where we want to use calculus to find the point xy on the parabola traced out by y equals x squared that is closest to the point 3, 0. So first you got to ask yourself, why is this in this section? And what am I trying to do here? So let's draw a picture. Okay, so here's our parabola. That's y equals x squared right here. That's our graph. And what we're trying to do is find the point on the parabola that's closest to this one. So we're trying to minimize something. So it should feel like we're trying to minimize something. And what is it exactly that we're trying to minimize? We want it to be closest. So that means that this line is going to be the shortest, or in other words, we're going to have the smallest distance. Okay, so our objective function measures the distance from a point xy on the graph of y equals x squared to the point 3, 0. So that's what our objective function needs to be. So here's our distance formula from xy to 3, 0. Okay, so we want to minimize this distance. And in order to make our lives a little bit easier, instead of finding the minimum distance, just because it's going to be easier to solve an equation, we're going to find the minimum of the square of the distance. That might be a little bit uncomfortable, but when you minimize the distance, you also minimize the square of the distance. When you minimize the square of the distance, you minimize the distance. Okay, they both have the same minimums. Okay, and then what else? Right now we have our objective function. It's in terms of two variables. We would like it in terms of one variable. So how are x and y related? That is what your constraint is. It tells you how x and y are related. They really do depend on each other. So you might have to ask yourself, can I use any old x and y? Are any x and y acceptable? And the answer is no. I couldn't say use the point 2, 0 because it's not on the graph of y equals x squared. I can only use a point on the graph of y equals x squared. So my constraint is that y equals x squared. So my new objective function is going to be x minus 3 squared plus x to the fourth. Instead of y, I'm going to write x squared, so I get x to the fourth. Okay. And so now I have to think about what my domain is of my objective function. Okay, it's all real numbers. Remember, x is just an x value for this parabola. Since y equals x squared has domain all real numbers, so does our objective function. And realistically, that point is not going to be really, really far away. But our domain of our objective function is all real numbers. And so we have to use the first derivative test or the second derivative test, and then hope that we only have one critical value or some other means to determine that we do have a global minimum. So we need to find the derivative of the objective function, and we get 2 times x minus 3 plus 4x cubed. And when we find the derivative of the objective function, we do this so we can find the critical values, which occur when the derivative is 0 or when the derivative does not exist. This derivative exists for all x values, so we don't get extra critical values that way, but we can't forget to ask that question. So we also want to know when it's equal to 0. So this is actually, the cubic can actually be difficult. So why don't we just look at this and see if we can find a 0, find an x value that gives us 0 on the left side. Maybe we'll divide everything by 2 and get 2x cubed plus x minus 3 equals 0. And hopefully you can look at this, just think about it for a minute, maybe press pause, and see that x equals 1 is a solution. If I substitute x equals 1, I get a solution to this equation. Okay, Since x equals 1 is a solution, we can factor x minus 1 out of the left-hand side, and in fact it factors as x minus 1 times 2x squared plus 2x plus 3 equals 0. So this second factor, 2x squared plus 2x plus 3, it doesn't give us any other, I didn't mean to do that. It doesn't give us any other factors and any other zeros, so x equals 1, that's our only critical value. It's the only solution to this equation. Okay. So we make a number line for our first derivative, and we're going to choose values on either side. So let's do that. Let's recall that f prime of x, that was 2 times x minus 3 plus 4x cubed. Domain was all real numbers. So let's pick a value to the left of 1. Let's say x equals 0. If x equals 0, then f prime of 0 is 2 times negative 3, or negative 6. So we get a negative f prime value. If x is larger than 1, let's choose x equals 3. That's going to be convenient for us. F prime of 3 is 2 times 0 plus 4 times 3 cubed. I don't really care what that value is, I just care that it's positive. That tells me that since f prime goes from negative to positive at x equals 1, that tells me that f decreases for all values up until 1 and increases for all x values after 1. That tells me that not only do we have a local minimum at x equals 1, we also have a global minimum at x equals 1. And since that is what's occurring, we have that of all the points on the graph of y equals x squared, the point 1, 1 is the closest to 3, 0 on the graph of y equals x squared. Okay? You might ask yourself, well, where did that extra 1 come from? I thought x equals 1 is the place that's the closest. Well, we're looking for the points on the graph of y equals squared. So if x is 1 on y equals x squared, so is y. All right, look for one more answer video to the optimization problems for class.